Okay, a couple pieces of important information here. This has a mass of 1,800 kilograms. This distance is 3.7 meters. And to answer the first question, which is find the maximum distance the spring, the first question is speed of the cab just before it hits the spring. Okay, so that's this location right here. And since they tell us how high it started from, I'm going to make this location A in my Uck-Wuck equation, and this is going to be location B. I also want to decide on where y equals 0. And one little trick, you can make y equals 0 anywhere you want to. However, if you make y equals 0 at the relaxed end of the spring, that's often helpful, and I think you'll see why later in this problem. So here we go. U at A plus K at A plus WNC equals U at B plus K at B. Well, the potential energy at A is going to be gravitational, so that's going to be 1,800 mass times 9.8 G times 3.7. That's how high I am above where I say y equals 0. It has no kinetic energy at that spot. However, between A and B, according to the problem, there is a 4,400 Newton frictional force. So we need to account for that with F cosine theta d. I'll fill that in later. On the far end of the equation, this is just before it hits the spring, it's going to have 0 potential energy because it's at y equals 0 and the spring hasn't been compressed yet. And we're interested in how fast it's going, 1/2 1,800 times speed at b squared. So let me do a few calculations. Let me plug in a few numbers. This here, when you multiply them together, you end up with 65,268. Now, the force is given as a frictional force. They say 4.4 kilonewtons. You multiply by 1,000, that's 4,400 newtons. The cosine of the angle, it's the cosine of 180 degrees. That's because the elevator is moving down, but friction is going to be in the opposite direction, 180 degrees in the opposite direction. And the distance is 3.7 meters, the given distance there. And half of 1,800 is 900 times v at b squared. So that's all you need to figure out the speed at b. You can do the math, and the answer is 7.4 meters per second. Okay, well, what's question B? Here we have to find how far the spring is compressed, this distance x right here. I'm going to call that point C, and we can set any 2 points equal to one another. I could set B equal to C or A equal to C. The Uck-Wuck equation works no matter what. I like to start with given information, so I'm going to start at point A again, 1,800 times 9.8 times 3.7, plus no kinetic energy, plus once again work is going to be done by friction, so we have 4,400. The cosine of 180 is -1. Now here, our distance is a little tricky. It's going to drop 3.7 meters, so that's in there. But then it's going to drop an extra distance, this distance x, how far the spring is compressed. So I have to say plus x. So that's something to be careful about. On the other side of the equation, also a little tricky here. It has some elastic potential energy for sure. I'm going to continue my equals over here. So that's 1/2 kx squared, 1/2 150,000 newtons per meter. They said 0.15 meganewtons per meter, so you have to multiply that by 1,000,000. 0.15 times 1,000,000 is 150,000, times the unknown x squared. However, there is also gravitational potential energy at this location because we are not at y equals 0. So that's m, 1,800, times g, 9.8, and in this case, times negative x. Negative because it's below 0. So those are some tricky little pitfalls you can run into. If you multiply everything together here, combine like terms, you end up with a quadratic equation. I'll just write down that final quadratic equation that you end up with. It's 75,000 x squared minus 17,640x minus 48,988 equals 0. So you can try that for yourself. You're going to have to then use the quadratic equation to solve that. You get two answers for x. One of them is negative 0.72 meters. The other answer is 0.90 meters. And in this case, the negative answer doesn't make sense. Why doesn't it make sense? Because then you would have a negative of a negative distance for the gravitational potential energy, and that would give you a positive distance. That would be above 0. So we're going to stick with the positive answer here. Okay, now we have part C. And in part C, they want us to figure out, well, once it's here, how far does it bounce up in the air? You know what? I'm going to erase all this. It's getting messy. And so again, we are at the totally compressed position, and we're being asked, well, how far is it going to bounce up in the air? Now here, I think it makes sense. It seems simpler to me to reset where I'm saying y equals 0. I'm going to say y equals 0 at that fully compressed position. That's going to be my A. And then, you know, when it bounces up again, the highest point that it gets to is going to be B. So let's try that. U at A plus K at A plus W and C equals U at B plus K at B. All right, at A, since y equals 0 here, there's no gravitational potential energy, but there's that elastic potential energy, 1/2 150,000. And what did we calculate the x was? It was 0.9 squared. So that's the that's the elastic potential energy it has at that location. Now work is going to be done by friction. Force of friction is 4,400 newtons. Cosine of 180 is -1. And then we have this distance that we're looking for. And I'm simply going to call that y. That's the y position. That's the final y position. On the other side of the equation, when it gets to the highest point, the only type of energy it'll have is gravitational potential energy. So that's m, which is 1,800 times 9.8 times y. And so that's the equation that you need to solve for a y value. If you do that, you should get 2.76 meters. And that's your answer to C. All right, finally, in D, it asks us, what is the total distance that this thing is going to travel? It goes down and goes up, and it goes down and it goes up. What's the total distance? So I'm going to, once again, do U at A plus K at A plus W and C equals U at B plus K at B to answer that question. Here, A is going to be way back to the very, very beginning of the problem. When it started from rest, 3.7 meters above the spring. And I hope it doesn't confuse you, but I'm going to go back to saying y equals 0 at the relaxed position of the spring. Again, just because I think it'll make my answer easier, or the math easier, I should say. So anyway, from the very, very start of this problem, it was 1,800 times 9.8 times 3.7, and it had no kinetic energy there. We're going to have friction again, 4,400, cosine of 180 is -1. Now it's an unknown distance. That's what we're trying to find. What is the total distance, back and forth and back and forth, added all together, that this thing moves? And then when's it going to come to a stop? It's not going to have any kinetic energy. It's going to be sitting on the spring, and here's the trick. It is going to be sitting at rest on the spring, and therefore the spring is going to be compressed just a tiny bit. So let's separately figure out how much the spring is going to be compressed. Here's the weight of the elevator. Here's the force that the spring exerts. Eventually those two things will be balanced as it sits at rest. So I'm going to use F equals kx. The F would be the weight of the elevator, 1,800 times 9.8. And the K is, of course, 150,000. And so we can then figure out what's the X going to be. How far is it going to compress that spring? And I'm going to do that calculation real quick here on my calculator. Maybe I'll pause. Okay, my calculator tells me that's 0.1176 meters. So now let's go back here. So when it's at rest, we have 1/2 K, which is 150,000, X squared, and that X is 0.1176 squared. But it's also not at y equals 0. It's a little bit below the relaxed position of the spring. So that's 1,800 times 9.8 times -0.1176. So that's the formula that you have to work out here to get an answer for distance. And if you round it off, it's approximately 15 meters.